Okay, so we're going to discuss two things today. We are going to discuss what it means for a function to be increasing and what it means for a function to decrease. Okay, and then we're going to figure out how to actually figure out when a function is increasing or when a function is decreasing. Okay. Okay, so a couple definitions, and I'll kind of walk through. These definitions are pretty formal for what it means for a function to decrease or increase. In general, we say that a function f is decreasing if for any value x1 is less than x2, we have f at x1 is greater than f at x2. Now, what that means, let's draw a quick picture for what this thing looks like. Okay, so it's saying, yeah, we have a function on an interval, or the function is decreasing on an interval if for any x1 less than x2 on that interval. So let's draw out a little picture of our function. So we have x1 and x2. And it's saying the function is decreasing if f at x1 is bigger than f at x2, right? So what this is saying is f at x1 is bigger than f at x2, right? So our function is doing something like this. Okay? And so it should be pretty clear that that function is decreasing, right? Really what that definition is saying is that the values of the function, the y values of the function, are getting smaller as we move from left to right on our graph. Okay? Now, the opposite is also true. If the values are getting bigger, it means that the function is increasing. Okay? So if we have a similar setup, we have some x1 which is less than x2. If we have it such that f at x1 is smaller than f at x2, so let's say we have something like this, then we can clearly see that the function is increasing, okay? Meaning the y values are getting larger as we move from left to right, okay? And so that's kind of like the formal definition of what it means for a function to be increasing or decreasing, okay? Now, oftentimes we don't really think about y values like this because we now have a better way of determining when a function is increasing and decreasing. And that actually comes from the derivative, right? So if we look at this graph here, we can see that at any point in this little interval here, we have f prime of 0, or sorry, f prime of x is less than 0, right? So the derivative of my function is negative. The slope of the tangent to this graph at any point between x1 and x2 is a negative number, right? And if we look at the increasing function, we see the opposite is true, right? If I pick any point along my interval here, I notice that f prime of x is greater than 0. Okay, and so these are actually the definitions that we're going to be using when we're trying to figure out if a function is increasing or when a function is decreasing. Okay, if the slope is negative, it's decreasing. If the slope is positive, it's increasing. All right, and actually I'm pretty sure we talked about, even very briefly, we actually talked about increasing and decreasing functions just sort of in passing, but now we can actually we have a way, or we will have a way of figuring out when a function is increasing and when a function is decreasing. Okay, so let's get into an example of determining where a given function is increasing or decreasing. Okay. Okay, so here I have a function, f at x equals x cubed plus 3x squared minus 2, and I want to figure out where this function is increasing or decreasing. Okay, so what I'll do for this question is I'll introduce kind of the routine that we're going to follow to figure out intervals of increase and decrease. Okay, so step 1 is actually going to be to find the critical points. Or find critical values, I guess. Okay, and finding critical values, again, we saw that last chapter. We do it every single time we do an optimization problem. We take the derivative, we set the derivative equal to 0, and then we just solve for the variables. Okay, so, or solve for the values of the variable. All right, so f prime of x in our example here is 3x squared plus 6x. Okay. And so to find the critical values, I set my derivative equal to 0, and then I solve. All right, so what I can do here is I can factor out a 3x. So 3x, and I'm left with x plus 2 equals 0. And this gives me two values, two critical values. X is either equal to 0 or x is equal to -2. Okay, so I have successfully found my critical values. All right. And what I can do from here is I can actually, you might have seen this in advanced functions. Actually, I'm going to switch over right now. Give me a second here. Okay, so step 2 here, I'm going to set up an interval table. Okay, so set up an interval table. All right, and the way that I construct my interval tables, I do the following. So Samarth, this might be a little bit different than what you're used to in advanced functions, because now we're really going to be focusing on the value of the derivative in our interval table. Okay, so along the top row of my interval table here, so in the top row, what I'm going to do is I'm going to do all the intervals and separate them according to my critical points. Okay, so intervals defined by crit points. Okay, so I will have basically my two critical points are x is equal to -2 and x is equal to 0. So I want to define my intervals based on those 2 points, right? So essentially the intervals that I create are x is less than -2, then x is between -2 and 0, so -2 is less than x is less than 0, and then anything bigger than 0. Okay, so I essentially split up the real number line based on where my critical points are. Okay. So then what I'm going to do, and again, you might have your own kind of method to how to set up these interval tables. I'm just going to show mine. Okay, so you can kind of figure out what works best for you. I like listing a test point here. Okay, so test points, I'm just picking numbers that are within each interval, right? So a number less than -2, let's say -4. A number between -2 and 0, so say -1. And then a number bigger than 0, so let's say 2. Okay, so those are my test points. Now what I can do is essentially what I'm aiming to do is find the value of my derivative at each of these test points. Okay, so I'm looking for what my derivative is equal to at these test points. Okay, mainly what I'm interested in is whether or not the derivative is positive or negative. Okay, so what I'm going to do is I'm going to evaluate my function at each of these test points. So I want f prime at -4. I want to figure out what that is. Okay, so I'm just going to pop open my calculator here. So 3 times -4 times -4 plus 2. I get a value of 24. Okay, and again, I don't necessarily care about what the number is. I don't care that my derivative is 24. All I care about is that the derivative is a positive number. Okay, so really what I'm focusing on here is the fact that, oh, well, this is positive. Okay, and then I'm just going to repeat for every interval that I have. All right, so I'm going to do the exact same thing, f prime at -1. I'm going to plug that in. So 3 times -1 times -1 plus 2. I get a value of -3. Okay, so again, I don't care that it's equal to -3, I just care that it's negative. And then lastly, I evaluate it at 2, so 3 times 2 times 4. I get a value of positive 24 again. So f prime at 2 equals 24. Meaning my slope, the slope of my function at 2 is going to be positive. Okay. And so what this tells me is that I can kind of summarize now, right? I'm pretty much done the problem. I've actually figured out where the function is increasing and where the function is decreasing. The only thing I have left to do now is just write a concluding statement. Okay, so 3, conclude. So we would say, therefore, the function is increasing. It's increasing over 2 intervals, right? It's increasing when x is less than -2 and when x is bigger than 0. So increasing when x is less than -2 or x is bigger than 0. You could also write this using, so this is written using interval notation. You could also use set notation, right? So you could say x is an element of anything less than -2. So we could say -infinity to -2. And we join that with the set 0 to positive infinity. Okay, so either notation is fine by me. You should, at this point, you should be pretty comfortable with both types of notation. If you haven't seen one, I'm sure you've seen interval notation because I've used it a lot. If you haven't seen the set notation, let me know and we can always go through it. Okay. And then we also, so the function is increasing on this interval and the function is decreasing between -2 and 0. So -2 is less than x is less than 0. Or again, we could write this in interval set notation. X is an element of all values between -2 and 0. Okay, and that's that. So I'll take a pause here. Let me know if you have any questions. Okay, so I have another function here. So g at x is equal to x over x squared plus 1. All right, and same idea. We're going to figure out when this thing is both increasing and decreasing. All right. So yeah, I'm going to just kind of blaze through the steps here. So 1, I need the derivative, so dg by dx. All right. Now here I have some sort of rational function, right? I have a function divided by another, and so I have to use quotient rule to get the derivative. All right. So quotient rule is going to tell me that I start with the derivative of the numerator, that's just 1, times my denominator, x squared plus 1, and then I subtract, I keep my numerator the same, and I multiply by the derivative of the denominator, so 2x. And then that entire thing is divided by the denominator squared. All right. But same idea here, I set this equal to 0 and I solve for my critical points. All right, so equals 0, and then I solve. All right, so one thing I notice right away, I can get rid of my denominator as long as, actually it's never going to be 0, so I don't have to worry about anything there. And so I'm just left with x squared plus 1 minus 2x squared equals 0, which means that I have 1 minus x squared equals 0, 1 equals x squared, or x is equal to plus or minus 1. And those are my critical values. Okay. So step 1 is complete. I found my critical values. Now I'm going to set up my interval table. Same as I did with the last question. Okay. So let's see where that'll get us. So 2, I define my interval table. So again, along the top, I'm going to define all the intervals split up with my critical values, my critical points. Okay. So I will have x is anything less than -1. -1 is less than x is less than +1, and then anything bigger than +1. Okay. And I'm interested in what the values of my derivative are at within each of these intervals. Okay, so again, if you'd like, you can pick some test points. Okay, so less than -1, so -2, maybe 0, and +2 as our test values. All right, I'm going to plug each of those in and see what we get. All right. But keep in mind, I'm focused on the entire derivative, right? So what I'm really evaluating here is I'm evaluating this entire function at x is equal to whatever my values of my test points are, right? So dg by dx equals, I can simplify this a little bit, 1 minus x squared over x squared plus 1 squared. All right, so that's what I'm plugging these test points into. All right. So let's plug in -2. So when I plug in -2, I get a negative value. When I plug in 0, I'm going to get a positive value. And when I plug in +2, I'm going to get another negative value. Okay. And then I just conclude. All right. Therefore, f at x is increasing between -1 less than x is less than 1, or x is between -1 and 1. And it's decreasing everywhere else. So when x is less than -1, or when x is greater than +1. And written in interval notation, it would be like this. All right, any questions based off that example? Okay, so in this example, we're actually given this graph is the graph of f prime of x, right? So the blue graph here is f prime of x. And what we have to do is we actually have to go backwards, okay? So we have to use the knowledge that we have about the derivative and actually unwind that to figure out what the original function would have looked like before we had taken the derivative, okay? And so there's kind of sort of ways to do this, right? So first of all, we know that Okay, so let's see how this, like, I want you guys to do these questions, and then we'll kind of take an integral, which is just a reverse derivative, and we'll see if we match up, right? So we're going to guess at what the function is, and then we're actually going to see if we guess correctly, okay? And I say guess, I mean like an educated guess, right? So the first thing we need to do is we essentially need to take inventory. So we need to ask, where is the function, where is the derivative equal to 0, right? And we have to figure out where is the derivative positive and where is the derivative negative, okay? So notice that f prime of x is equal to 0 at x equals, so what is that? About negative 0.6. And at, that looks like, yeah, positive 3 there. Okay. So our function would probably be something like x plus 0.6 and x minus 3. So that looks like a pretty good function. Okay, and then we also need to know f prime of x is negative, so smaller than 0. I'll do some color coding here. So our derivative is negative, kind of in this region right here. So that's where our derivative is negative, and then our derivative is positive up here and up here. Okay, so f prime of x is negative between, so when x is between negative 0.6 and 3. And then f prime of x is positive outside of that interval. So when x is smaller than negative 0.6 and when x is bigger than 3. Okay, so what this information tells me is it tells me where my original function was going to be decreasing, right? So the function is going to be decreasing here. Decreasing. The function is increasing here. Okay. And then at negative 0.6 and at 3, the function is neither increasing nor decreasing. Okay. And so the way that I would do this when I set up my graph here. So I'm going to indicate kind of the two main points here, my critical points, right? So negative 0.6, and again, this is going to be a rough sketch, so it won't be perfect. 3. Okay, so I'm going to indicate these points like this. Okay. Okay, so essentially, I'm told that my function is decreasing between negative 0.6 and 3. So my function might be doing something like this. Okay, so I can see that any point, actually let me make that a little bit more clear. Okay, so I can see that any point within that interval there, my slope would be negative, which is exactly what I want, right? Now when x is bigger than 3, or when x is smaller than negative 0.6, I'm increasing, right? Which means my y values are getting bigger as I keep going, okay? And so my function could look something like that, right? Again, I notice that I am increasing here, and I am increasing here, and I am decreasing in the middle, okay? And then at the two critical points, right, I notice that my slope is 0, right? So at those 2 points, I'm neither increasing nor decreasing, okay? Now, Samarth, you correctly mentioned that this would be some kind of integral, right? And so what we can do, let's see if we can do this. So f prime of x is x squared minus 3x plus 0.6x minus, what's 0.6 times 3? 1.8. All right, so I can clean up this function, and then I'll take an integral. All right, so I get x squared minus 2.4x minus 1.8. Okay, so that's df by dx. Okay, so the way that I take an integral, it's kind of like a reverse derivative. Okay, so you have to imagine what function would you have to differentiate get back to the original function. Okay, so this is going to seem kind of weird, and I'm not really going to explain the rules, but then what we'll do is we'll go into Desmos and we'll compare the function that I'm about to get with what we've drawn here to see how close we got. Okay, so the way that this works, I'm going to actually, I want to show you the correct notation here. So I have df by dx. And so what I'm going to do is I'm going to integrate both sides. Okay, so what I'll end up getting, and again, I'm not being super formal here, but what I'll end up getting is f at x is equal to x cubed over 3 minus 1.2x squared minus 1.8x. And then here's the really weird part about integration. We don't get like an actual exact function, right? We get a range of functions that could work. And what we have to do to indicate that is we introduce like a parameter or a constant, this plus c. That plus c is called the constant of integration. Okay. Now, what you guys can check, if you guys want, what I would recommend doing here is take the derivative of the function that we just found. So differentiate x cubed over 3 minus 1.2x squared, blah, 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 blah. And what you'll get when you do that is you'll actually get back to this original function that we found, okay, or the original equation for the derivative. All right. So let's actually graph this in Desmos, and let's see how close we got. Okay, so let's get to 4.2 now. 4.2 kind of summarizes a lot of what we've sort of already been talking about. So the first thing, or I guess the one new thing perhaps, is this first derivative test. Okay, so the first derivative test basically states that if we know that a point is a maximum value, right, or we're trying to show that a critical point is a maximum value, then what we'd be able to notice, I'm just going to draw some like random function in between there, right? What we would notice about this function is that if we look before the critical point, we would notice that f prime is positive. And if we were to look after the critical point, then f prime would be negative, right? Meaning that if a function goes from increasing to decreasing, then the point in the middle has to be a maximum, okay? F prime of x less than 0, okay? Now this also goes for the converse, right? If I go from decreasing to increasing, so again I'll draw out a little function here. Again, my critical point, my slope is 0, but if I look before the critical point, I would notice that my function is decreasing. So f prime of x before the critical point is negative. And if I look after the critical point, I would find that the derivative, f prime of x, is positive. Okay. So essentially for a maximum, if I'm dealing with a local max, my function switches from increasing to decreasing. If instead I'm dealing with a local min, my function goes from decreasing to increasing, okay? And if I try to do this and I can't, or I get something like my function goes from increasing to increasing, then it's not a maximum or a minimum. It's some other type of point, which we'll see in a bit, okay? Okay, so let's give this a try, shall we? So for the function, I'm just going through the example here. So we have a function y equals x to the 4 minus 8x cubed plus 18x squared. We have to first determine all the critical numbers, and then determine whether each of these critical numbers gives a local max, a local min, or neither a local max or a min. Okay, so let's see what's going on with this. So again, first step first, I have to figure out the critical numbers. All right, so I'm going to take the derivative and I'm going to set it equal to 0. All right, so I have 4x cubed minus 24x squared plus 36x. All right. I can factor out an x. Oh, I guess I can factor out a 4 and an x from each of these terms. So 4x times x squared minus 6x plus 9. Okay. And then I could continue to factor, right? I notice here I have a trinomial and I can factor that. So in this trinomial, I notice that I want to multiply to 9 and add to negative 6. So that'll just be negative 3 and negative 3. Okay, so negative 3, negative 3. So we'll get 0 equals 4x times x minus 3 times x minus 3. Okay, or 4x times x minus 3 squared. Okay, and so I have two critical numbers, right? The two values that make this thing 0 are x equals 0, right? 0 times x minus 3 is 0, or positive 3, right? So I get two critical numbers, x equals 0 or x equals 3. Okay, so I found my two critical values. Okay, so crit values. All right, now that I have those critical values, I want to figure out whether or not these represent maximums, minimums, or something else entirely. Okay, so let's set up an interval chart. Okay, so one thing I will say throughout this chapter, you guys will be seeing tons of interval charts. Basically, every question will call for you guys to make an interval chart of some kind. Okay, so same as how I have been doing, right? X is less than 0. X is between 0 and 3, and x is bigger than 3. So let's see what the value of our derivative is in each of these intervals. So I'll pick some test points. So we'll say -2, 1, and 4. All right, let's figure out what f prime is at each of these test points. Okay, so I'm just plugging into my derivative formula for each of these. So 4 times -2 cubed minus 24 squared 36 times -2. So I plug in -2 and I get a negative value. Let's see what happens when we plug in 1. So 4 minus 24 plus 36. I get a value of positive 16, so that's positive. Let's plug in 4. So 4 times 4 to the power of 3 minus 24, 4 squared. And when I plug in 4, I get another positive. Okay, and so the way that I interpret this interval chart, I am decreasing here, increasing here, and then increasing again here. Okay, and so if I look at this this first point here, right? So when x is equal to 0, I go from decreasing to increasing. Okay, so my function is going to look something like this. My function is decreasing, then it reaches the critical point, and then it's increasing again. Okay, and so what this tells me is that I'm dealing with a local minimum. Okay, because I go from decreasing to increasing. All right. If I look at x equals 3 here, I'm not going to get something like that, right? So what I end up getting is I go from increasing, and then I flatten out, right, because it's a critical point. The slope is 0. But then I continue increasing, okay? So I actually get, this is not a max or a min, so neither a max or min. What we call this is we call it an inflection point. Inflection point, or point of inflection, point of inflection. Okay, so I go from increasing to increasing. It's neither a max nor a min. Okay, and so that's how the first derivative test works. You figure out where your critical points are, and then you kind of determine whether or not you go from decreasing to increasing, or increasing to decreasing, or neither. Okay. Any questions based off that example? Or are we all good? Okay. Yeah, let's see another quick example of this inflection point here. So I'm given y is equal to x to the power of 3. So y is equal to x cubed. So I have my basic cubic polynomial here. So again, if I do y prime, I get 3x squared. I set y prime to be 0. And what I find is that when I solve for 0 here, I just get x is equal to 0, right? However, when I look at this function, I notice 3x squared. 3x squared is always bigger than or equal to 0, right? And what that tells me is this function will never decrease, right? Y is equal to x to the power of 3 will never decrease. And so there is no way of getting a maximum or a minimum if the function will never decrease, right? And so what ends up happening here is, again, I get a similar scenario to what happened in the previous problem, where I go from increasing to increasing, okay? And so what ends up happening, and again, I'm sure you guys have both seen the y equals x cubed, the basic cubic polynomial by now. It looks something like this, right? So we have boom, and then we have a point like that, and then it keeps increasing like this, right? Y equals x cubed. So again, we get a point of inflection right in the middle there, okay? So essentially, the main takeaway from these two examples, just because our derivative is 0, just because we have a critical point, does not guarantee that we have a max or a min, okay? We could have something else. We could have like a point of inflection, okay? And towards the end of this chapter, we are going to figure out another test that allows us to figure out whether or not, or what kind of point of inflection we have, okay? So for that, we'll actually need the second derivative, and we'll talk about the second derivative test, but we'll get to that, okay? Okay, so that was a quick little example, and then last example here, okay? So, and this is actually the reverse of the example that we did before, right? So the other graph that we were given, that was the derivative, and we had to work backwards to figure out what the function was. With this graph, what we're doing is we're doing the opposite, right? We're going forwards. We have a graph, and we have to figure out what the derivative looks like, or the graph of the derivative looks like, okay? But I can still apply some similar techniques here, right? So if I look at, so here it seems like I have a turning point, so I have a minimum, and my minimum is at x is equal to 0, And then it appears as though I have a maximum at x is equal to 1. Max x equals 1. Okay. And so if I break up this this function here into essentially I have 3 intervals that I have to kind of pay attention to, right? So I have the interval when x is less than 0. I have this little interval in between when x is between 0 and 1, right? And then I have everything that's bigger than 1, right? X is bigger than 1. So those are the 3 intervals that I'm considering, okay? Now, when I look at the slope of my tangent line over each of these intervals, what I find is that, okay, so when x is less than 0, I note that f prime of x is negative, right? My function is decreasing over that entire interval, okay? When I'm right in between here, when I'm between 0 and 1, again, if I focus on the tangent line in this zone, what I find is that f prime of x is greater than 0, meaning my function is increasing there. Okay? And then when I look at any point for x bigger than 1 and I draw my tangent line, I notice once again I am decreasing, right? So f prime of x is less than 0 because I am decreasing. Okay? And so what this kind of tells me is it actually will tell me how to draw my derivative, right? So let's go to the derivative here. So I'm going to create a new axis. Okay, so let's fill in all the information that we have here. So I'm told that I have a minimum at x is equal to 0, right? So my minimum and my maximum for that matter, both of these tell me that f prime of x is going to be equal to 0 at those 2 points. All right, so if I come to my graph, I go to x is equal to 0 and x is equal to 1, and I know that my derivative will have to pass through those points. Okay. Now, in between those 2 points, I know that I'm increasing, right? So between 0 and 1, I know that my function, I know that my function is increasing, which means my derivative is positive, okay? And so what that means is my derivative has to be above the x-axis here. My derivative is positive, right? Now, outside of that interval, I know that my function is decreasing. And so the fact that my function is decreasing tells me that my derivative has to be negative after that, right? So outside of these points, I'll have something like this, right? Because my derivative is negative. My function is decreasing. Probably make that look a little bit nicer, maybe something like that. It's pretty rough. And that is what f prime of x might look like. Okay, so yeah, quick little example, but again, I would say the more practice problems you do with this stuff, you'll kind of get the interval tables and whatnot. And yeah, any questions about that one?